Okay, good morning. How's everyone doing? Ready for the weekend? Quiz on Monday is going to be light. Light. Yeah, low fat. It's going to be low fat quiz. First things first, there's a lot of things going on today for me professionally. So there's a workshop seminar I'm attending until 2 o'clock, right after my class ends at 12. And then there's a industrial advisory board meeting going on all day in the E department. So I won't be able to have office hours, not in person. I'll be able to answer emails and perhaps meet over Zoom maybe between 4 and 5. Or I might, if I'm in the office between 4 and 5, students can come in then also if they wish to. So I just wanted to announce there. And I'll also, post the announcement on the website also for students who may not be here. But I just wanted to say that before I forget. So today is without any hyperbole, one of the most important talks, okay? Because if students don't understand what we do today, then the rest of the quarter is going to be a blur, okay? And we are looking at chapter 5. So let me bring up the class notebook. We're talking about chapter 5, where we introduced the time varying sinusoidal waveforms. And then the point I made was the voltages and currents in a time varying circuit or time varying source circuit requires the solving of differential equations, which we saw in chapters 3 and 4 also, right? For an inductor, the voltage is L di over dt, derivative of the current. If you wish to find the voltage, then you integrate the current. So you perform derivation and integration on all sides. So rather than do that, what we can do is we can use complex numbers. So this entire chapter is about using complex math, okay? It's not a new analysis technique. Again, there's only 3 analysis techniques, okay? You have Ohm's law, you have KVL, and you have KCL. Those are the only 3. Because node voltage analysis is a combination of these 3. Mesh current analysis is also a combination of these 3. Thevenin and Norton is a concept that uses these techniques. So analysis techniques, again, chapter 5 is all about the math, okay? And personally, I find that math beautiful. We use complex numbers to actually make the math less complex. And I'll show you how and why. What we're going to do is we will represent the sources, meaning the voltages and currents, as complex quantities, and we will represent the impedance. We will represent inductors and capacitors as complex quantities known as impedances. So let's first talk about voltages and currents, okay? For any voltage or any current, a sinusoidal waveform looks like this, right? And we looked at the standard expression, Vm cos of omega t plus theta. If it's I of t, it has the same structure. I of t is Im cos omega t plus theta. Theta can be positive or negative. Depends on the perspective, okay? It could be positive or negative. It's like saying you are either ahead of somebody or behind somebody. But the same situation can be applied depending on how you are viewing things, right? So in the same way, we take the time domain representation and we are going to transform it into a rotating vector in the complex plane. A rotating vector in the complex plane. So this time domain representation is now represented as a vector. The vector is known as a phasor. And the transform is known as a phasor transform. We don't do the derivation for non-E major classes. But the implementation is very simple. It's straightforward, okay? So again, we do a phasor transform and you represent it as a phasor. That phasor is a vector. It's a rotating vector, but it is simply a single snapshot. It's a single snapshot of one instant in time, which is right here, when it crosses the y-axis. That's all it is. Okay. So we have our time domain expression, Vm cos of omega t plus theta. A vector only needs two things to describe itself, right? Magnitude and direction. So we need the length of the vector and the angle it makes with the real axis. We are now in the frequency domain. In the complex plane, we have a real axis, we have the imaginary axis. So we represent that vector, and the vector only needs two things, length and the phase angle, and you obtain both of those directly from the time domain expression. Vm or Vp, the peak value of that quantity on the y-axis, gives you the length of the vector, and the phase shift, or the phase in the time domain in degrees, gives you the angle it makes with the real axis. Yes. Vm is the length of the vector. So this Vm is the length of that vector. Okay, length of the vector. This is the symbol, as a symbol or representation for a phasor for voltage. It's kind of like an uppercase V with an incline, and there are some, I want to call it like, studs at the top. There's a technical term for that, but I can't remember what it is. This right here, you see those tiny studs at the top. So it's easy to read in print, but hard to like write it out. Anyway, that's the phasor for V. Phasor for voltage is the magnitude of the voltage, Vm, with a phase angle theta. It does not, even though it's a rotating vector, as I said, a vector, that phasor is just a single snapshot in time. Single snapshot in time. We say it's rotating counterclockwise. So from the real axis, this is the real axis, this is the imaginary, and this vector is rotating counterclockwise. If the vector rotates counterclockwise, the angle it makes with the real axis is positive. A negative angle is if it goes below in the opposite direction. So it rotates clockwise and you get a negative angle. So as I said, plus 90 can be written as minus 270, right? It's one single circle, one full cycle. So one pie of pizza, one circle. But, and again, it's a poor joke and a poor pun, if you will. One full circle is not one pie, it's two pie. Maybe somebody should start a pizza chain, two pie. Okay, so as I said, there's a phasor transform we do, but we don't, again, there's a derivation. If you're interested, stop by my office. I can, I'd be happy to show it to you. But when we want to do a phasor representation, all we do is we take the magnitude, we take the phase angle, you directly write out the phasor. Yes. Oh, yeah. Positive, negative, VE. Positive, negative. This VE, right? This VE. Yeah, positive, negative. That's all it is. Yeah, I have some acronyms that I've been used to, so I don't think about those, but thank you for asking. Yes. So what was I saying? Oh, yeah. So those are the polar coordinates. Again, we remember we're talking about maths, right? So the polar representation is the polar coordinates of the vector. If you project the vector on the real and the imaginary axis, you get the rectangular coordinates. So if you extend, not here, if you extend a vector on the real axis, which is right here, you get A. You extend or project that vector on the imaginary axis, you get B. And you can get, or you can obtain, the rectangular coordinates. So R with the length R with a phase angle theta becomes A plus or minus JB. And J represents the imaginary number in electrical engineering. I is, of course, reserved for current. And so we use J in electrical engineering. Now, I would like to make a note that all of the math that we look at here is not specific to EE. It's just math in general. So as engineers in your own field, if you have not yet encountered this, you will at some point. Okay. So this math is generic. Excuse me. This math is generic in the term that it applies to all scientific fields. You can apply this math anywhere. Okay? It's not just electrical engineering or AC analysis. So let's go back to our slide. As I was saying, we take the time domain expression, transform it into the frequency domain. In the complex plane, we represent it as a vector. So now, what do we do with that? Let's see. As I was saying, this is one full cycle, right? One full cycle is one circle. It's 1 pi, but mathematically in radians, of course, is 2 pi, right? 2 pi. Circumference of a circle, 2 pi r. So in radians is 2 pi, or because it's a circle, it's 2 pi or 360 degrees. This is 2 pi, 0. 1/2 cycle is pi, or 180 degrees. And then a quarter cycle is pi by 2, or 90 degrees. Straight up imaginary axis, okay? So the relationship between the angle in radians or in degrees. And if you remember, I said there's a reason why we keep the phase in degrees separate, because we want the phase shift to describe the angle for that vector. Okay, that's the reason we keep it separate. One final important note is that the expression, the time domain expression, must be in cosine. It must be in cosine. If you look at the vector, what is it? It is a right angle triangle, right? It's a right angle triangle. In trigonometric identities, that's where it comes from. So if you have a expression in sine, you have to convert it into cosine. Right angle triangle, the right angle at the far end is 90 degrees. The other two angles, add them up, plus 90. So sine of x is equal to cos of x minus 90. The cosine of the other angle. Anyway, the phasor transform, if you wish to apply phasor transform and write the phasor directly for any voltage or current, your expression must be in cosine. Simple subtraction. You take the quantity and you subtract, or you take the phase angle for that voltage or current, and you subtract 90 degrees from there. You shift the phase. So sine of x becomes x minus 90. So that's the vector representation for the voltage or current. Okay. Now here's an even more important topic. It's impedance. So again, don't worry about writing a lot of it down. I mean, you already have access to the slides, but I will go over what the concept is in brief, and then, mathematical representation, the equations. Let's look at just the English word. Resistance comes from resist. What is resist? Resist is the opposition to the flow of current. Hence resistance. Okay? Opposition to the flow of current, hence resistance. Then we have a new term, reactance and impedance. Reactance, of course, comes from the word react, and there is a reason for that. I will explain that. Impedance, what does it remind you of? Impede, kind of synonymous with resist. Okay, so that's, if you think about it, the words are synonyms of each other, and so is the deal with impedance, resistance, and reactance. They're all kind of synonyms of each other when it comes to AC analysis. Okay, so having said that, let's talk about reactance first. Capacitors and inductors are energy storage devices. Resistors do not have any energy storage capability, right? Resistors straight up resist or oppose the flow of input current. Capacitors and inductors do not. They do not resist any flow of the input current or oppose any input voltage. However, because they are energy storage devices, what happens is the energy is stored in the magnetic field, energy is stored in the electric field. This stored energy will oppose any change in the input quantity. Again, it is not resisting the input quantity, but it opposes any change in that input quantity. Meaning if the input quantity is constant, no opposition. But the moment it starts changing, as it does in AC, then it opposes any change in that quantity. And that has a physical manifestation. It is not resistance, hence we call it a new term known as reactance. It is reacting to the change in the input quantity. Let's take a pause, you think on that. Let me know if you have any questions. Yes. That is correct. Question being asked is if reactance is only valid for AC, and the answer is yes. And we will talk about it qualitatively and quantitatively. Just the next few points. Yes. Any kind. As a practical example in real life, if you take a look at any speakers, whether it's a home theater in a box or you buy a separate speaker, you look at the spec sheet, it'll say impedance specification, because a speaker is nothing but a coil of wire in a magnet. Any kind of speaker, whether it's a small earphone or whether it's a big, large subwoofer, it always has a coil of conducting wire around a magnet. So that's an inductor. Inductor will have impedance. The signal that goes to a speaker is varying. The frequency varies. Even the sounds that I'm making right now, captured by the microphone, it's taking the sound waves and converting into electrical signals. A speaker does the exact opposite. It takes the electrical signals, it goes through the inductive coil, sets up the magnetic field inside the magnet, and the variation in the frequency as well as the amplitude of the signal changes the magnetic field, which manifests as vibration of that speaker. That's how it reproduces the sound. And so the opposition for that coil, that speaker coil, to any change in the input is represented as the impedance. In real life, in real life, as you just asked for the example, in real life, we usually never talk in terms of reactance. We always talk in terms of impedance. But right now, I just explained what reactance is. So any questions about reactance? And then we'll go over impedance. Again, recap. Reactance is not direct opposition to current or to voltage, but it is the opposition to change in the input current or change in the input voltage. Okay, that is termed as reactance. Mathematically, we represent it using complex numbers. More specifically, we represent reactance with the imaginary number. We represent it using the imaginary number. And when you combine resistance and reactance together, you obtain what is known as impedance. The representation symbol for impedance is Z. Resistance, of course, is R. And reactance with X. And so impedance is a complex quantity, a complex number. Mathematically speaking, it's a complex number represented by R plus JX. R is the real part of impedance. X, the reactance, is the imaginary part of impedance. An important follow-up note. When we state real part and imaginary part, it's not a figment of somebody's imagination. Reactance has a physical basis in real life. It is very real. The mathematical representation is imaginary. So you would often hear the words or read the words imaginary reactance or imaginary part of the impedance or the real part of the impedance. It is purely talking about the mathematical representation. Okay, reactance is not imaginary. It is real, has a physical basis, but imaginary reactance simply means imaginary numbers. And that is given by R plus JX. Right, let's take a pause. Think over that. Let me know if you have any questions. Any questions? Okay. All right. So then I said impedance, reactance, and resistance are kind of all synonyms of each other, right? Mathematical representation plus also some physical explanation. But the symbol for all of them is exactly the same. And so are the units. The same symbol as we use for resistance and the same units, ohms. Okay. Now, remember what I said about, I think that goes back to the point that some question that somebody asked earlier, right? Reactance is only for inductor and capacitor? Yes, because it has to do with the stored energy. So if there is no stored energy, there is no reactance, meaning a resistor does not have any reactance. So if you write ZR, there is no such thing as ZR. There is no such thing as impedance of a resistor because the resistor behaves for AC exactly the same way it behaves for DC. It obtains energy. Electrical energy is converted to thermal energy and dissipated as heat. Resistors get hot. So this would be R plus J0, simply R. Okay. So ZR is just R. Ideal inductors and ideal capacitors, on the other hand, do not have any resistance. So it is 0 plus JXL, which is simply JXL. XL is the reactance of the inductor. And then ZC is simply 0 plus JXC. So it simply becomes JXC. It's actually not plus JXC, it's actually minus, but I will explain why it's minus. Okay. Equations for ZL and ZC are given here, and I will go over them in a little bit. What I want to point out is the polar coordinates of the impedance. You have R plus JX, right? Real portion and the imaginary portion. So those give you the rectangular coordinates. If you transform them into polar coordinates, you get a vector, right? You get a vector. This is the opposite of the phasor. For the phasor, you had a vector and you projected it on the real and imaginary axis. Now you have the real and the imaginary values. And now if you combine them together, you get a vector. That vector, the length of the vector gives you the magnitude of the impedance, and the angle it makes with the real axis gives you the phase. This is not a rotating vector. Okay, it's not like a phasor. It's simply a vector in the complex plane. That's all it is. It has length and it has an angle. Magnitude Z, phase angle theta. So you combine all three sides, you get what is known as the impedance triangle. Impedance triangle. Okay. You have R on the real axis, on the x-axis. You have X on the y-axis. And the third side, the hypotenuse, gives you the magnitude of Z, the impedance triangle. Now, for a inductor, energy stored in the magnetic field opposes any change in the input current. So because it opposes change in the input current, the current will always be behind the voltage. The voltage will come first, the current will follow later. And that is graphically represented like this. This is the voltage for an inductor, and the current for the same inductor will be 90 degrees behind. Remember, I said pi by 2. Right? This is IL. And if you remember, x-axis is always time. Positive values, meaning going towards your right, going towards the right, you are in the future, you are behind. Going towards the left, you are in the past, meaning you are ahead. So voltage for an inductor always leads the current for that inductor by 90 degrees. Doesn't matter what the inductor is, doesn't matter what the circuit is, doesn't really matter what the source is, doesn't matter what the value is for either the voltage or current. The phase difference between the voltage and current of an inductor, of one specific inductor, not with relation to anything else, just for that inductor, is always, always, always plus 90 degrees. Yes. Inductor. This is just inductor. So this is just inductor. And then we look at for capacitor also. So keep this in mind. This is going to give you theta VL minus the phase for IL is always going to be plus 90. Always going to be plus 90. For a capacitor, it's flipped. For a capacitor, the voltage, remember, voltage is the input. If you apply a different voltage, if the voltage tries to change, it will oppose the electric field, the stored energy will oppose any change in the input voltage. So the voltage changes later. So the voltage lags the current in a capacitor. So C, if this was IC, I made a hash of that. Okay, this would be VC. So in this case, VC lags and IC leads. Okay. And so here, theta VC minus theta IC is going to give you minus 90. Always, 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 always. Doesn't matter what capacitor it is, doesn't matter what the voltage or current is. The voltage and current for a specific capacitor will always have a phase difference of minus 90. Okay. Now, Eli Manning, some of you know, he's a quarterback for the New York Giants. No, he's known as the Iceman because he had ice in his veins. Not really. This mnemonic predates him. What do L and C stand for? Inductor and capacitor. I, of course, is for current. Take a wild guess what E stands for. It's voltage. EMF, electromotive force. So for a inductor, the voltage is always ahead of the current. For a capacitor, the current is always ahead of the voltage by 90 degrees. Voltage leads current, and for capacitor, voltage lags the current. All right. So now I want to explain why this is important and the meaning of this minus 90 and plus 90 in these equations for the inductor impedances. Okay. If we take a look at, so this, I will go over the math operations a little bit, but the whole point of doing all this math is, and as I stated, we use complex math to make the math less complex. If you have a circuit, you apply a voltage or a current, time varying, right? Cos omega t, sine omega t, whatever. If you now want to solve the voltage or current for an inductor or capacitor, you're performing differentiation, you're performing integration, differential equations, right? So instead of doing all of that, if you just simply represent everything using complex numbers, you can apply all of the techniques exactly as they are written. Ohm's law, KVL, KCL, everything simply works because of the beauty of complex numbers. I have to take the magnitudes into account and the angles, and everything just works. Meaning you no longer have to do L is equal to L di over dt, or integrate the voltage to find the current. You simply apply Ohm's law, which is V equals IR, except instead of R, everything is now replaced by its equivalent impedance. For a resistor, R remains as it is, so it's V equals IR. For an inductor, instead of doing L di over dt, you simply do IL times ZL. Same thing for a capacitor, IC times ZC. And that's the beauty of using complex numbers. You can apply everything exactly the way it was. Imagine how much fun node voltage analysis would be if you have complex numbers in the mix. So KVL, KCL, everything works exactly the way it is. But what I wanted to point out was this. V equals IZ. That means Z, the impedance, is V over I, where V and I are both phasors. Z, I, and V are all complex number representations. So everything is a vector. V and I are the phasors, and Z, of course, is the complex impedance, right? So if you have a division of two complex numbers, you have magnitude of Z with the phase angle of Z, the impedance. You have magnitudes of voltage divided by magnitude of the current. What happens to the phase angles? Anyone? They get subtracted. So theta V minus theta I. That's the standard equation, right, for impedance. Z is V divided by I, always. That doesn't change. So impedance for any quantity, whether it's resistor, inductor, or capacitor, will always have theta V minus theta I. The numerator minus the denominator. So phase angle of the voltage minus phase angle of the current. 5-second pause while you write that down. Yes. Sure. So yeah, so that's basically the mathematical operation. And I will go over the mathematical operation in the previous slide. No, the phase angles get subtracted. The numerator minus the denominator. So this would be magnitude of V divided by magnitude of I, and theta, the phase angle of the voltage, divided by the phase angle of the current. Yes. It depends on the component. For a resistor, there is no difference in the phase. So phase angle for a resistor will always be 0. Hence, the impedance of a resistor is always the magnitude resistor. I will go back to that slide. Yes. So hold on to that question. You're talking about for the inductor and the capacitor, right? Yeah. So I will go back to that slide. Yes. Because once we see this, then that slide makes a lot more sense. So mathematical operation, we'll come back to that. And then for your impedance, we'll just look at it in the next few seconds. So again, as I was saying, Ohm's law, V equals IZ. So Z is V divided by I. Everything is a complex number. And so you have phase magnitudes being divided. You have phase angles being divided. When you divide phase angles, the math operation is the numerator minus the denominator. That's the actual math operation. Okay. So when you have theta V minus theta I, if you look at the impedance for an inductor, theta V minus theta I is always plus 90. Hence, the impedance for an inductor will always have a plus 90 angle. That's where that comes from. And hence, the equation for ZL has an angle of plus 90. Similarly, for a capacitor, the phase difference of voltage and current is always minus 90. And because it's minus 90, the phase angle, the impedance of a capacitor will always have a minus 90 angle. And that's where that comes from. Hence, the impedance for a capacitor is always going to be minus J over minus J times XC. Okay, so this is minus J. Okay, minus J. All right, let's take a pause. Think on that. Let me know if you have questions. Does that answer your question about the plus and the minus 90? All right, think on that. Any questions before I move on? Yes. Mhm. So the question being asked is, if there are multiple components, would they still be 90 degrees apart? The answer is yes and no. It's yes if you are referring to the same component. No if you're referring to two different components. Meaning, for example, let's say if you have a inductor L1 and inductor L2, the voltage and current for inductor L1 will always be plus 90 apart. The voltage and current for inductor L2 will also always be plus 90 apart. But the voltage for inductor L1 and the current for L2 may or may not be 90 apart because it's two separate components. So it depends on the circuit configuration in that case. So if it's the same component, then yes. If it's two separate components, then maybe no. All right. Any other questions? Okay. All right. So let's look at the math. Now, the reason I show this math is, well, it's useful. This is how we used to solve it before we had programmable calculators. And my calculator is from the 90s. Okay. Yeah, that old. That's when I first started out as a student, and it still works. It cannot be programmed. The only thing I can do in there, well, I can do a lot of things, but with regards to complex numbers, I can do a polar to rectangular conversion and a rectangular to polar conversion. When you have equations, you might have equations in rectangular numbers, rectangular coordinates divided by polar coordinates, plus or subtracting like another polar coordinate number. You can program all of that into a programmable calculator, and it would spit out one single value, like one step answer. But if it's a long equation, you need to be an expert at programming that, because if you make one tiny error, entering a plus or a minus sign, then your entire answer would be invalid. Okay. So again, if you have not yet looked at the online worksheet, I strongly advise and recommend that you do so as soon as possible. Otherwise, the rest of the quarter is going to be a blur. Okay. Students need to be an expert at using their own calculators. So go ahead and do that. Now, before the advent of programmable functions, this is how we used to do the math operations. Remember, we are equations, right? So we have to multiply and divide or add and subtract two complex numbers, two or more complex numbers. So it is easier to perform addition and subtraction if you have two rectangular numbers or two numbers in rectangular coordinates. And it is easier to multiply and divide if the same numbers are represented using polar coordinates. Let's take rectangular first. Rectangular is rather straightforward. If you have two numbers that you're either adding or subtracting, all you're doing is you're combining the real parts together and you combine the imaginary parts together. So again, addition or adding and subtracting two complex numbers is easier if you have rectangular coordinates representation. Multiplication and division, and that's the answer to your question, is if you have two complex numbers and you're multiplying them, magnitude with phase multiplied with C and D, the magnitudes are multiplied together and the phase angles are added up or summed up. Okay, the magnitudes are multiplied here because it's two vectors. It's two vectors, right? So magnitudes are multiplied, phase angles get added up. If you're dividing two complex numbers, the magnitudes are divided and the phase angles are subtracted. Numerator minus the denominator. That's the mathematical operation. This comes from trigonometry, right? It's a vector, so it's a right angle triangle. You can perform any mathematical operation in any coordinates system, but it is easier if you perform addition and subtraction with rectangular numbers and multiplication and division with polar coordinates. Does that answer your question? Kind of. We just leave it as it is. We just leave it as it is, yeah. When we perform the inverse phasor transform, we can simply take the final magnitude and final angle and just write the cos omega t expression directly from there. That depends on whether we are looking at impedance or, let's say this is voltage divided by current, then we'd either have to calculate them or they would be given to us, like any normal circuit. Possibly. Or it could be two impedances in parallel, two impedances in series. We'll look at in examples. Yeah. Right now, we are just looking at the math. We are not looking at actual circuit scenarios. But there's a couple more slides, so let's get to those. We looked at fundamental laws, KVL, KCL, everything works as it is. The only difference is KVL, KCL will work, not just magnitudes, but we have to account for the phase angles also, right? So let's say you have a circuit and you're applying 10 volts AC to it. Let's say this is 5 ohms, 3 ohms, and 2 ohms. If it's a DC, you straight up 5 volts, 3 volts, and 2 volts, right? If you plotted DC voltages as vectors, they don't have any angles. You could plot these as 0, 0, 5 volts, right? You plot the second one, where the first one ends. So 3 volts. And then you plot the third one where the second one ends. And then the start and the end point gives you the total source voltage, 10 volts, that's being applied. Make sense? That's DC. For AC, you have to take the phase angles into account. So this is DC. And for AC, so in the lab, this is what you're going to do next week for lab 6. You're using KVL to verify whether everything works out, phasor diagrams. Okay? Does that make sense? So oftentimes you just measure the voltage in the lab, but all you're doing is you're measuring the magnitude. If you simply add up those voltages, they won't make sense. KVL will not add up because we are not taking the phase angles into account. We cannot measure those. We have to calculate those. Okay. Okay, only a minute left. If you have to leave, you can go ahead and leave. I'm going to finish this up. There's only 2 more slides. If you have multiple inductors and capacitors in a circuit, you cannot add those up. But when you transform them into impedances, inductor can be represented with inductor impedance. Capacitor can be represented as ZC. So, even though you might have an inductor and capacitor in series, you cannot add them up, you cannot combine them, but you can combine their impedances. Inductor in series would be represented as 2 impedances in series, ZL and ZC. So ZEQ is ZL plus ZC. Okay. Then similarly, if you have an inductor or capacitor in parallel, allergies and a sore throat, watery eyes. Okay. One last slide. Reciprocals of impedance, reactance, and resistance. Resistance, resist. Reciprocal is conduct, conductance. Impede, admit. React, susceptible. The reactance, susceptance, resistance, conductance, impedance, admittance. Oftentimes, it is useful for us to work with reciprocals when we're working with parallel circuits. And so it makes it easier for us to perform mathematical operations. Okay. And so if we already have the reciprocals before we begin our circuit analysis, we simply add them up. So we don't have to actually perform complex math. Makes it easier for analysis. The symbols for all of them are noted here. We won't actually use any of these quantities, actual problem solving in 201, but it's something that you'll encounter in the lab. Okay, so I like to have a slide that covers these terms. The units named after German physicist Siemens, sometimes also referred to as mho, simply the reverse of ohm. Okay, apologies for going over time, but this is where we'll end class today. We'll have a quiz on Monday as usual. I'll post the announcement later today, just based on chapter 5, not on 4. Okay, chapter 5. And then again, no office hours at the usual time. I can answer by email or over Zoom, and perhaps in person between 4 and 5. All right, have a good weekend, and we'll see you all on Monday.